The capabilities of a transport category aircraft are not static numbers printed in a manual. They represent a live, shifting mathematical optimization problem. Every time an aircraft lines up on the runway, its operational envelope is actively recalculating based on the immediate physics of the surrounding environment. The limits of what an aircraft can achieve during takeoff, climb, cruise, and landing are governed by the strict interplay of aerodynamic forces, the rate of kinetic energy absorption, and a series of precisely defined reference velocities. Pilots interface with these physical limits through critical v-speeds. Looking at this airspeed indicator, we see specific marker text that represent the exact aerodynamic edges of the aircraft's operational envelope. Speeds like vref dictate the landing approach, while v1, vr, and v2 dictate the precise sequence of acceleration, rotation, and safe climb-out. Each notch is a calculated boundary between safe flight and a loss of control. While standard operations give these limits a wide berth, the true test of the performance envelope occurs during worst-case scenarios, like a catastrophic engine failure mid-flight over jagged, high-altitude terrain. To understand how these aircraft safely navigate these extremes, we need to decode the v-speeds, break down the strict takeoff limits, analyze the physics of climb profiles, and examine the fluid dynamics that threaten a safe landing. Mastering aircraft performance requires translating absolute physical limits into the rigorous regulatory mathematics that ensure operational safety margins. A safe departure is framed by three critical v-speeds: v1, the decision speed; vr, the exact rotation speed; and v2, the takeoff safety speed used to establish the initial climb if an engine fails. v1 is the aerodynamic point of no return. As the aircraft accelerates past this exact velocity, the pilot must commit to flying the aircraft, even if an engine suddenly fails. Below v1, the takeoff must be rejected. This decision speed operates within strict physical boundaries. Its absolute lower bound must be greater than vmcg, or minimum control speed on the ground. If an engine fails, the asymmetric thrust will cause a massive yawing moment. The aircraft must be moving fast enough for the rudder to maintain directional control. Conversely, V1 has an absolute upper bound, VMBE, or maximum brake energy speed. An aborted takeoff requires the brakes to absorb millions of foot-pounds of kinetic energy. If a reject is initiated above VMBE, the brakes will exceed their thermal capacity and catch fire before the aircraft stops. This graph illustrates the concept of a balanced field takeoff. We are plotting the takeoff distance required to clear a 35-foot obstacle on one engine against the accelerate stop distance required to bring the aircraft to a complete halt. The exact intersection of these two curves visually defines the optimal V1 speed for a specific weight. At this point, the distance required to safely stop precisely mirrors the distance required to safely continue. This intersection defines the minimum usable runway length. By pinpointing this equilibrium, V1 and the balanced field length perfectly balance the extreme kinetic risks of maximum effort braking against the aerodynamic risks of climbing out on a single engine. Hitting that optimal takeoff speed is entirely dependent on the aircraft's weight. But maximum takeoff weight is never a guaranteed figure. It is strictly capped by the most restrictive of 6 distinct certification factors. First is the structural limit. This is a fixed weight constraint based on the physical strength of the airframe, the load capacity of the wings, and the structural limits of the landing gear. Second is the climb limit. This ensures that even with one engine inoperative, the remaining thrust can meet the mandatory minimum climb gradients required by regulations. Third is the obstacle limit. The calculated departure path must clear all physical terrain and structures beyond the runway by a vertical margin of at least 35 feet. Fourth is the field length limit. The balanced field calculations we just discussed must actually fit within the physical dimensions of the runway's declared distances. Fifth is the brake energy limit. As established by VMBE, the takeoff weight cannot exceed the thermal absorption capacity of the brake assemblies during a high-speed abort. Finally, the tire speed limit. A heavier aircraft requires higher ground speeds to generate lift. This limit prevents the wheels from spinning so fast that centrifugal forces rip the tire carcasses apart before liftoff. These 6 limits do not exist in a vacuum. Environmental variables continuously shrink these margins. High temperatures and low pressure combine to create high-density altitude. This thin air drastically reduces both the mass airflow entering the engines and the lift generated by the wings. Secondary variables compound these performance penalties. Tailwinds force the aircraft to achieve higher ground speeds to reach necessary aerodynamic speeds. Uphill runway slopes introduce a rearward component of gravity opposing engine thrust, and standing water or slush introduces severe displacement drag against the tires. Allowable takeoff weight is an unforgiving daily calculation that relentlessly penalizes the aircraft for every single adverse environmental factor present on the runway. Once airborne, the focus shifts to climb performance. Efficiently gaining altitude requires targeting one of two very specific airspeeds, depending entirely on the immediate objective. This graph plots aircraft drag and thrust against velocity. Vx is the best angle of climb. It is the exact airspeed that yields the maximum altitude gain over the shortest horizontal distance, used primarily to clear immediate obstacles at the end of the runway. Looking at the curves, Vx occurs at the specific velocity where the aircraft has the maximum excess thrust available. That surplus thrust is applied directly to fight the downward vector of the aircraft's weight, resulting in the steepest possible climb angle. In this updated graph, we overlay power available instead of thrust. Vy is the best rate of climb. This speed yields the maximum altitude over time and is used to reach cruising altitudes as quickly as possible. Physics defines power as a force applied over a velocity. Therefore, Vy occurs at the airspeed yielding the maximum excess power. While the climb angle is shallower than Vx, the higher forward speed means the aircraft is climbing at a faster rate in feet per minute. As the aircraft climbs, air density steadily drops, reducing engine performance. To maintain peak aerodynamic efficiency, heavy transport aircraft utilize step climbs, leveling off to burn fuel and reduce weight, before thrusting up to a higher, thinner altitude. Vx and Vy are not arbitrary throttle settings. They are precise mathematical optimizations of available thrust and power, constantly plotted against the changing curve of aerodynamic drag. The most critical en route contingency occurs if an engine fails while cruising above the aircraft's single-engine absolute ceiling. Without the thrust of that lost engine, the aircraft cannot maintain its altitude and is forced into a gradual descent. This forced descent is called a drift down. The pilot must manage the aircraft's pitch to maintain VYSE, the one-engine inoperative best rate of climb speed. In this scenario, VYSE provides the minimum rate of sink, stretching the glide as far as possible over the terrain below. This graph illustrates the descent over mountainous terrain. The upper curve is the gross flight path, representing the aircraft's actual physical descent rate. But for dispatch planning, we must look at the lower curve, the net flight path. Aviation authorities require dispatchers to penalize the aircraft's actual twin-engine drift-down performance. By law, they must subtract a 1.1% climb gradient from the gross flight path to calculate the net flight path. This artificial penalty is mandatory. It guarantees a mathematical safety buffer, ensuring that even if the atmospheric conditions underperform or the engine degrades, the aircraft will still clear the terrain and reach an alternate airport. Surviving a drift down isn't just about clearing the rocks below, it's a complex navigation problem. Maximizing horizontal range to that alternate airport requires calculating exact ground speeds through surrounding weather. This vector diagram shows the nonlinear wind correction angle equation. Ground speed equals the square root of true airspeed squared minus the crosswind squared minus the headwind. A strong crosswind imposes compound penalties. To track straight toward the runway, the aircraft must adopt a crab angle into the wind. That angle geometry actively reduces the forward velocity vector, lengthening the time it takes to reach safety. En route safety does not rely on best-case scenarios. It relies heavily on artificially handicapping the aircraft's actual performance to guarantee a mathematical buffer over hostile terrain. As the aircraft clears the terrain and begins its final descent, operations are bracketed by two extremes: VNE, the never-exceed structural speed limit, and VREF, the reference landing speed. VREF is the critical approach speed target over the runway threshold. It is rigidly calculated as 1.3 times VS0, which is the absolute stall speed of the aircraft when fully configured for landing with gear and flaps down. Landing performance relies on a direct comparison between the landing distance available on the runway and the landing distance required by the aircraft's weight. But this simple comparison becomes infinitely more complex the moment water is introduced to the tarmac. This diagram shows a tire rolling through standing water. If the tire cannot displace the fluid fast enough, it induces hydroplaning. This introduces severe displacement drag and can instantly sever the tire's friction with the asphalt, eliminating directional control and braking efficiency. The most common type is dynamic hydroplaning. At high rollout speeds, the tire is forced to ride entirely on a wedge of standing water. The rubber completely loses contact with the runway, dropping friction effectively to zero. Viscous hydroplaning can occur at much lower speeds. A very thin film of water mixes with accumulated rubber dust or oil deposits on the touchdown zone, creating an impenetrable, slippery seal that prevents the tire from gripping the microtexture of the pavement. The most destructive form is reverted rubber hydroplaning. If a wheel walks up during a skid, the intense friction boils the underlying water into a pocket of high-pressure steam. This steam lifts the tire and literally melts the rubber tread right off the carcass. To counter these severe fluid dynamics, dispatchers and pilots use the Runway Condition Assessment Matrix, or RCAM. Slippery, contaminated conditions reported on the runway trigger strict performance penalties, sometimes applying a 1.92 multiplier to the dry landing distance just to ensure the aircraft can stop in time. From the aerodynamic point of no return at V1 to the fluid dynamic calculations of a wet rollout, aircraft performance represents an unbroken, heavily regulated chain of physics, engineered to keep every flight safely inside the edges of the envelope.